Okay, so let's do non-conservative system. So let's do one of these. Non-conservative system. Okay. So let's see. We're gonna have here an inclined plane right here, and we're gonna have a particle at the top. We have a particle at the top, little box here at the top of our plane. We have an angle theta, which is going to be equal to 30 degrees. It's going to be 30 degrees for theta. And this particle is going to slide down. It's going to go this way. It's going to slide down and it's going to pass through the point A here. And we want to know what is the velocity. What is the velocity at point A? Okay. And it's come this way. This is the path. Okay, comes this way. And the thing here is that there's going to be friction. So you're going to have friction on the surface right here. So what you have here is a system where the initial energy is equal to the final energy minus the work done by friction, because friction is going to be a new force that wasn't there before, but it's going to show as soon as this little box starts moving. It's going to start to move from rest. And we're going to give it a mass of 2 kilograms. The mass is going to be 2 kilograms. And we know that G is 9.8, of course, is going to be 9.8 meters per second square. We know that. That's gravity. And the height is going to be 15 meters right here. So you're going to have your height right here. This is going to be your height. And your height is going to be 15 meters. 15 meters right there. And you have your coefficient of kinetic friction. Your coefficient of kinetic friction is going to be 0.2, has no units at all. So that's going to be 0.2. That's your coefficient of kinetic friction. So what do we have? Well, we do have that 1/2 of the mass velocity, initial velocity to the square, plus mgh is equal to 1/2 of the mass final velocity, which is the velocity in the point A, to the square, minus the work done by friction. It's going to be friction times the distance x on the x, the distance on the x-axis. And this is going to be the work. This is going to be the work done by friction. This is going to be the work done by friction. Friction is a force. And if you multiply the force times the distance, you will get your work done by friction. And that's going to be this path right here. This is your dx. So that's going to be your dx. This is going to be your dx, which is that distance from here to here, which is the hypotenuse of your triangle. Okay, so the initial velocity is going to be 0 because this guy is going to start from rest. So this term goes away, it cancels out, and you only have mgh is going to be equal to 1/2 of the mass velocity at the point A, that's where you want it, minus the friction times the displacement in the x direction. So we need to do a body diagram to find out. I'm going to do my body diagram right here. Let me do it with this one over here. This is going to be your body diagram right here. And you're going to have, here's your body diagram. And this is going to be your x direction. And this is going to be your y direction. So you got your x direction right here. And the particle is going to be at the center. Your particle is right here at the center. And you have a friction force that goes this way. So that's going to be the friction right there. And then you got the normal force that goes this way, the normal force. Let's do the normal force right there. Okay, you got this. Okay, let's do this axis in another color. Let's change the color for the axis right here. Okay, here we go. There you go. And we're going to have a normal force. Goes this way, the normal force. Let's call it normal force. And then you're going to have the weight coming down this way. There's your weight. And okay, here's the vector of your weight. And then you have an angle theta here. Theta is going to be this angle over here. This is going to be theta. And theta is this one over here too. So that's your angle theta. That's your theta right there. Okay, so you have your component that goes this way. You have a component that goes this way, which is mg sine of theta. And the other component that goes this way, the green one right here, is going to be mg cosine of theta. And then mg sine of theta is going to be the acceleration. But right now, what we really need is the friction. So we have that, we have the normal force going this way. So the normal force minus mg cosine of theta is going to be equal to 0 because there's no acceleration in the y direction. All the acceleration is in the x direction. So n is going to be equal to mg cosine of theta. And we know that the friction is going to be the coefficient of kinetic friction times the normal force. So the friction is going to be mu k, which is the coefficient of kinetic friction, times mg cosine of theta right there. Let's make it a little more explicit here. Okay. So it's going to be, the friction is going to be the friction, your friction. Okay, your friction is going to be equal to mu k mg cosine of theta. And there you go. You got your friction. And we can calculate the distance dx, because the sine of 30 degrees is going to be equal to the opposite, which is the height, which is 15 meters, divided by dx, which is the hypotenuse. So dx is going to be 15 meters divided by the sine of 30. So dx is going to be equal to 15 meters divided by 1/2, because the sine of 30 is 1/2. So dx is going to be equal to 30 meters. And now you have everybody. So let's go back to our equation. Let's do it over here. Our mass is 2 kilograms. And we're going to multiply times 9.8 meters per second square. And the height is going to be 15 meters. And that's going to be equal to 1/2 of the mass, which is 2 kilograms. And we have velocity in the point A, which is what we're looking for, minus. And we have our friction, which is, let's calculate our friction. Okay, we can calculate right here. So if we plug 0.2 here, and then the mass is 2 kilograms, and then 9.8 meters per second square. And then this is going to be square root of 3 divided by 2. You're going to get a friction of, the friction is going to be 3.4 newtons. That would be your friction right there. 3.4 newtons. It's 2.2. Okay, it's let's do here everything correctly. It's going to be 0.2 that multiplies 2 kilograms times 9.8 meters per second square times the square root of 3 divided by 2. So it's going to be 3.4 newtons times 30 meters. And the only variable you have is the velocity, which is what you're looking for. That's the only thing you have left right here. So if you multiply 2 kilograms times 9.8 meters per second square times 15 meters, what are you going to get? Well, you're going to get 294 joules is equal to, well, this 2 is going to cancel with this 2. So you only have kilograms right here. And VA to the square is what you're looking for. And then minus 3.4 newtons times 30. So that's going to give you 102 joules. 102 joules. And now you have 294 joules plus 102 joules is equal to kilogram velocity NA to the square. Velocity NA to the square. Okay, let's do this one a little more appealing. So it's going to be kilogram velocity NA to the square. Yeah, because the 3.4 multiplied by 30 is Newton meter, turns into joule. It goes to the other side, it goes positive. So you add those guys, you got that. And now we can do it over here. So if you add these 294 plus 102, you get 396 joules over kilogram if you pass the kilograms, and then you got to get the square root of this, and that's going to be the velocity NA. And this is joules. Don't forget, this is joules. This is joules over kilogram. And if you do that math, you're going to get 19.9, let's say 20 meters per second. And 20 meters per second would be your velocity at point A. For a non-conservative system, that is a system where you're losing energy because energy is turning into heat because of the friction. Thank you very much.